And there is a counterexample in this case. If we select a very large number of mu, for instance, if you select mu equal to 1,000 and you select a very long simulation period, then the problem cannot be solved because there are some numerical issues which prevent you to perform this kind of task. And this kind of equation is actually referred to as the state differential equation, and I will explain it later to you. So do not run the code like this. Do not run the code because it will take quite a long time and then start saying not enough memory, no matter what is the size of the memory, it will give prompt like this. So this kind of equation is also called the state differential equations. And for this kind of equations, there are special solution methods for it. So I will explain this part later to you. Now let's consider a differential equation set. How can we convert a differential equation set like this into the standard form? Because we need the standard form to solve it numerically. We cannot solve this kind of differential equations automatically or with any other method. So what we need to do is for x, we select several state variables. For instance, here is the absolute, so we have to select m state variables. Then for y, we should select another n variables, but it starts from x to the m plus 1 and plus 2 to m plus n. We have to select a set of state variables. And with these variables, we can convert the original problem into a standard form like this. And it is exactly the same as the one here. So we can finally solve the problem in numerical method. And there is an example, which is a hollow satellite trajectory problem. And this mathematical form is always given in differential equation books. So how can we solve this kind of differential equations? To solve the differential equations, we have to select that x1 equals to x, x2 equals to x dot, x3 equals to y, and x4 equals to y dot. And we can write the whole equation into this form. And here we have variables r1 and r2. And r1 is a function of x1 and x3, and r2 is also a function of these two variables. So to calculate the left-hand side of the equation, we have to calculate r1 and r2 first. Then we can use this formula to calculate the left-hand side of the equation. So in this case, we cannot use the anonymous form because there are intermediate calculations required. We have to calculate R1, R2 first, and then we can calculate the left-hand side of the equation. So we cannot use this form. The only way to use is the .m file. So for this particular problem, we have to write a Matlab function like this to describe the original differential equation. That is to calculate R1 and R2 first, and then use this command to calculate the left-hand side of the equation. And for this differential equation, we can use the following commands to solve it. So, use the extra t somewhere. That's quite strange. So the time required is 0.08 seconds. can easily find the result. And here, I want to draw the relationship between y1 and y3. Actually, it should be for x and y in the original equation. And there are 689 points calculated. I will explain this topic later to you, how many points and how it is selected. I will explain it to you later. And this is the result of test. And there is a big problem. How can we check whether this one is correct or not? Because there is no analytical solutions, so we cannot check it in that way. So this one is very important, how to validate it. Let's go back to the mathematical formulas. So in this formula, if we select a step, the calculation step, we know x0 and we can select the calculation step, then we find the x1. This is one of the steps. x2 and there is another step. In each step, we have to calculate 6 values of ki's, and then we can calculate for the x vector of the next step. And there might be errors. So, in other words, I can interpret this part in another way. Although Matlab is not calculated the problem in this way. I think in this way you may understand the problem better. Suppose we know this point and we select a step like this. This is h. Through calculation we can find the x k plus 1. This is xk. And if we select a calculation step like this, we can find the value of the next of x as the next step, like k equals k plus 1 times. And this is the approximate solution, of course. How can we check whether it is correct? Now, if we break the step into two, and if we perform calculation, we can calculate and find these 2 points. And if the difference between these 2 values are small, which is smaller than any specified value, which for instance we have 10 to the power of 6. If it is small enough, then we say that this result is accurate. We can regard it as an accurate result. If the error is too big, then we have to, based on this step, we have to break the step into another 2 and find the difference and find the error between the 2 methods and see whether the error is small enough. Is this inequality satisfied, then we can use this step, otherwise we should use the other one. Maybe we should break it into halves again. So this one is quite useful. It will be used to model the intermediate result. So this one is quite useful. So how can we check whether the result of 10 is correct or not? We should use such